Try it. Good exercise. Okay. You can calculate the escape velocity of any particular object. You can calculate the escape velocity of a human being, of a human. A human has a mass of 100 kilograms, a radius of about 1 meter. This is kind of a big human, but we'll go with it. Let's see. V escape is equal to 2gm over a half. There's a very famous book about physics with the title Assume a Spherical Cow. And this is the kind of thing that physicists like to do. It's an idealized situation. We have this perfectly spherical human being. Okay, so let's do the calculation. 2 times 7 times 10 to the minus 11 times 100, that's 10 to the 2 over 1 to the square root. That's 14 times 10 to the minus 9. Call it 1.4 times 10 to the minus 8 to the half power. That's something like 1.2. Let's call it 1 times 10 to the minus 4 meters per second. Or, let's see, that's 1/10 of a millimeter per second. That's less than 1 meter per hour. And that's why we don't go into orbit around each other, okay? Because you're always moving way, way, way faster than the escape velocity of the people you're interacting with. The escape velocity of the Earth is 10 kilometers a second, so you're not moving that fast, so you're bound to the Earth. But when you're hanging around with your friends, you're probably going faster than 1 meter per hour, and therefore you're moving faster than the escape velocity. You don't feel a great effect of the gravitational force of other people. This is kind of an anti-Valentine's Day calculation, right? Because it proves that human beings are not attracted to each other. At least not by the force of gravity. And so you can do this calculation for any given object. Fine. So what's a black hole? Black hole has actually a very simple definition. A black hole is simply something in which the escape velocity is greater than or equal to the speed of light. C is the expression for the speed of light. This is 3 times 10 to the 8 meters per second. And if you've got something where the escape velocity is greater than the speed of light, that's what a black hole is. And it makes a certain amount of sense. If the escape velocity is greater than the speed of light, then light won't escape this object, so you won't be able to see it, right? Because the way you see something is you see the photons that come off it. And there's nothing particularly extraordinary about this as far as it goes. In fact, in the middle of this was already talked about and worked out in some detail in the middle of the 18th century by an otherwise obscure English clergyman named, I think, John Mitchell. And he did the following calculation. He said, okay, now, if this is going to be true, how big is such an object? How dense does it have to be? And you can work this out. Supposing the escape velocity is equal to the speed of light, so c is equal to 2gm over r to the 1/2 power. You can square both sides and regroup, and you have r is equal to 2gm over c squared. This is now, it wasn't called this in the 18th century, but it's now called the Schwarzschild radius. Schwarzschild was a contemporary of Einstein's. And this is the size something has to be in order for its escape velocity to be equal to the speed of light. And a black hole, another definition of a black hole, is something in which the radius of the object is less than the Schwarzschild radius. Because if the radius is less, then the escape velocity will be even greater. So, as I say, this was worked out in obscurity in the middle of the 18th century, and nobody thought anything much about it. Mitchell sort of pondered for a little bit what such an object would look like, and he decided it would look dark. And true enough, but who cares? Nobody thought anything further about it for 150 years. Until Einstein came along at the start of the 20th century and came up with the theory of relativity, and one of the important pieces of relativity is that the speed of light, this c, is a very, very special velocity and has rather bizarre and extremely profound properties. And it was only at that point that the concept of the black hole was recognized as something that was in any way out of the ordinary. So for 150 years, this idea kind of lay dormant until it was resurrected by a profound change in the thinking about the underlying physics. So this is one of these kind of historical fables that we've hit a couple of times. This is the fable of Mitchell's discovery of black holes. And the moral of this little fable might be that the importance of a result changes depending on the context of a result changes sometimes dramatically with context. So something that looks quite unimportant for a long time can all of a sudden become a very big deal. And so it happened in this case. Okay, so one question you can ask is, that's all fine. How big is the Schwarzschild radius for some bunch of objects? Let's try the sun. Here, let me start a new piece of paper. So how big is the Schwarzschild radius of the sun? Schwarzschild radius, again, 2gm over c squared equal 2 times 7 times 10 to the minus 11. Mass of the sun now 2 times 10 to the 30 divided by c squared. C is 3 times 10 to the 8, and we'll square it. Okay, so let's see. 2 times 2 is 4 times 7 is 30. 30 times 10 to the 19. 30 minus 11 is 19. Divided by 3 times 3 is 10. 10 to the 8 squared is 10 to the 16. So that's 3 times 10 to the 3. Because 19 minus 16 is 3. Oh, in meters, because we're still in MKS units, because that's what we're using. That's the units of G that we've chosen. 3 times 10 to the 3 meters, that's 3 kilometers. That's pretty small for the sun. And so you might imagine that such objects are rare or perhaps even non-existent, because it would have to be incredibly small and therefore incredibly dense to have a strong enough gravitational field to prevent light from escaping. And so you might have thought that this is an entirely theoretical concept and that no matter how interesting it is, there's no point in really studying it further because you're unlikely to ever encounter one of these things in real life. But one of the strange things that has been known for quite some time is that black holes really should exist, and that they are predicted to exist. And this has been known for quite a while, known for at least 70 years. 70 years, that black holes should exist. And the reason they should is that they are one of the possible endpoints of stellar evolution, the evolution of stars. And so now I want to summarize how stars evolve. I should say this is the subject of whole courses. You can take Astro 350, and they will talk about this for the entire semester. You can take Astro 110, and they'll talk about it for a month. But we're going to do it in about 20 minutes, save you time and effort here.